We are taking you behind the scenes of the National Institute for Data Science and Artificial Intelligence.
With unprecedented access to the scientists pushing boundaries and shaping our future, this show will take you to the cutting edge and beyond.
And whether you're an expert yourself or just science curious, this is the show for you.
Welcome to the Turing Podcast.
Welcome, everyone, to another episode of the Turing Podcast. I'm Anneca, and I'm here with my co-host, Bea, and we'll be talking to Zoe Kourtzi, who is a professor of computational cognitive neuroscience at the University of Cambridge and is also the Turing University lead there.
Hi, everyone. We're very interested to have here Professor Zoe because a team that was led by her has developed machine learning tools that can detect dementia in patients at a very early stage. So welcome to the podcast.
Great, thank you. Nice to be here and nice to meet you all.
So, Zoe, can you tell us about some of the current problems with diagnosing and treating dementia?
Yes, so dementia is really a very debilitating disorder. Many families, there are no families that have not touched by it these days. And the main problem is really that every patient is different. They have a different history. They have a different background in terms of health and in terms of lifestyle. And dementia starts about 10 to 15 years before we see any symptoms. So the diagnosis currently, based on the tools we have, is actually quite late, not early enough to be able to intervene successfully in most cases. And so the fact that we can only diagnose quite late and with quite invasive tools, and the fact that the symptoms have started earlier and they are very heterogeneous, makes the diagnosis and the detection of the disease a quite challenging problem.
So that's really interesting because that means that basically when it's detected, it's already too late because it had 10 to 15 years to activate. So how does this tool, this AI, help the diagnosis?
Yeah. So the aim is really to go as early as possible to make the diagnosis, maybe even before symptoms occur, and to make it as precise as possible, but also to make it as comfortable as possible for patients. Currently, the way that dementia is diagnosed is initially, patients will have some symptoms and they will go to their GP, they'll have some assessment, first assessment, then possibly referred to a memory clinic to have further assessments, and then a course of rather invasive measurements and assessments start. So first I'll have an MRI, which actually it's quite simple and pretty straightforward. But then if this is not diagnostic enough, then they will have more invasive scans, for example, a PET scan that requires radioactive activity, and then they'll have potentially lumbar punctures. This is a quite long trajectory of sometimes years before there is a precise diagnosis. Now, during this period, people usually will experience more symptoms, and these symptoms will get worse because of anxiety. So when somebody is diagnosed with dementia, given that we know that there are no disease-modifying treatments at this point, although a lot of progress is currently being made. People will be sent home with a potential diagnosis, but not much that can be done. And therefore, anxiety will increase actually their symptoms, because once you start getting anxious, your cognitive abilities will start being impaired. So you'll be more anxious, you'll sleep less well, you'll maybe not eat very well, and therefore then you can't remember, you're more confused. So a very difficult trajectory. So what we are trying to do with the tool that we built is detect dementia from very basic assessments. So this tool, thanks to thousands of patients that have given their data, has been built on a lot of cases of patients across different countries, and has seen a lot of types of data. So some basic cognitive assessments, some brain scans, but also a lot of what we call biomarkers. And these are recorded with much more invasive technologies and medical tools. Now, because the model is trained and because it has had all of this vast experience and rich experience from many patients, currently, when a new patient comes in, we don't require all of this data. What we require is one brain scan, which is the least invasive brain measurement that we can take. And that's a structural scan that looks just at the structures of the brain and how well defined they are at any stage of the disease. And that's typically about 5 to 10 minutes in a basic MRI scanner in a hospital. And then the model will look at these scans, and because it has learned from all of these other patients to learn associations between these scans and some cognitive assessments that all the patients would have had after being referred to a memory clinic, the model can make an initial prediction about the patient and can tell us whether this patient is showing signs and risk of dementia, and how quickly potentially they are moving down the trajectory of dementia pathology. So it makes the diagnosis much faster, earlier at the disease stages, and in a more precise way.
I feel like our entire generations just got a bit depressed with the idea that anxiety makes it worse, because we all went, oh no, this is terrible for all of us. I have a question. I don't know if this is going to be very out of it, but you've mentioned that you have a very large data set that you've taken this from. Did you manage to make this data set as diverse as possible? Because we've had a lot of issues in AI where the data sets are very biased towards one group of people.
This is really a big challenge. And we are kind of lucky enough now to have data sets that that can be accessed. But we're still very early days. So the data set that we worked on is a data set from the US, and it comes from people scanned at different sites in the US, 4 different sites. So some diversity, but really what we need to be looking here is more population diversity, and that really has not been done. We have tested this tool in the UK, and we have tested it in research studies, and now we are testing it in clinical populations. And we are building with the Turing collaborations, for example, in Australia and in Singapore, to start really increasing the amount of data, but also the diversity in this data. So this is really, really key. We are doing together with the Turing, we have a large scale collaborative program with the Alzheimer's Research UK, the EDON initiative, where we are recruiting cohorts from across the globe to mine the data, but also even more excitingly to collect lots of digital data from wearable technologies, so that we can go even less invasive in terms of collecting data from our everyday interactions in the environment, and much earlier, because data from wearable technologies can give us indication about changes that are happening in how people sleep, in how they walk, how they navigate their environments, how they breathe. And this could be really important data if we see a change in this data to couple with scans, for example, brain scans, to start diagnosing the disease as early as possible, but also with the diversity of really a large population across the globe. And then the least invasive our methods, the more kind of, if you want mobile and wearable type of methods we can use, the more we will be able to really develop tools for the global population. I always say that dementia is a global problem, so we really need global solutions, and therefore we need algorithms that will look at data from people across the globe.
It's really positive to hear. Thank you. I did have a question on other tools that are in existence. How is it separate? How is it different from other tools in existence?
It's really exciting to see that there are lots of people interested in this problem. And it's really exciting to see that, people coming now with a machine learning expertise, they're working together with biologists and neuroscientists to really develop tools. So there's more and more happening. I think the difference is that most of the times when we develop machine learning algorithms, we care a lot about their accuracy. And of course, we are kind of performance hungry. So we want to see our algorithms performing, 90, 80%. the difference here is that we really built this tool to be biologically relevant and clinically relevant. So where we are going with this is really we want to see it being translated into clinical practice. So this is not, if you want, about what's the best accuracy that we can achieve. We do want the algorithms to be accurate, but primarily we want these algorithms to be interpretable. And therefore, in this case, we have gone not for very deep algorithms, but kind of more shallow algorithms that we can interrogate them and understand why they make a prediction. And so that means the data that we put in the algorithms, then we can see, if you want, how they are kind of rank ordered in terms of their contribution to the disease trajectory of each individual. So this is one aspect that is a little bit different in terms of these algorithms are very interpretable and easy to interrogate, and we believe that this is really important for clinicians to trust them, because this is a big kind of a public health component. We really need our clinicians to feel comfortable with AI. We really need to be able to interrogate our tools and trust them, as these tools will be supporting them in their decision process. The other kind of, if you want, kind of unique thing about these algorithms is that they don't stop at the stage of classifying people and detecting the disease, but they look at individual trajectories. Because what we need to be able to do is to see how fast people progress towards dementia, or maybe not. So the first stage of the detection, we try to be as precise as possible to reduce misdiagnosis, because there's quite a lot of misdiagnosis, given that people might be suffering from many other diseases, for example, cardiovascular disease or diabetes or even depression. And that shows up as cognitive problems that look like dementia. So moving kind of beyond this initial, if you want, classification of patients as having dementia or not, we look at their trajectories and we see how fast they move towards dementia. And this can make a big difference in clinical pathways. So although we don't have disease-modifying treatment, we have interventions, for example, even lifestyle interventions that we can apply. And we need to know who are the patients that need the interventions now or later, and who are the patients that need hospitalization now or later. And so what the models this model allows to tell us, first of all, who are the patients that are stable, actually, and they will not potentially develop the disease. And these patients maybe need to be going into a completely different care pathway, because they might have other disorders that can be treated and cured, and therefore their dementia symptoms will hopefully go away. Then for patients where we see that there is risk for dementia, we can see whether they are moving slowly and therefore send them back in the community with some support, or whether they are moving really rapidly towards dementia and therefore need immediate hospitalization. This is really important for the patients, but it's also really important for the NHS, because currently we put people through many diagnostic tests because we don't have a good diagnosis to start with. That means a lot of funding, a lot of resources go to everybody and not to the people that really need it immediately. So with these models that give us this kind of trajectory, we can see who are the people that need it urgently, and we can tailor the resources towards them. And of course, for people that don't need immediate hospitalization, but they are early stages, there is lots of recommendation for changing lifestyle factors that can really help and hopefully slow down the disease for considerable more healthy years. So in that way, really, the unique thing about these algorithms is that really they are interpretable, increasing trustworthiness of machine learning. They are also generalizable because they were built in research data, but now we see that they generalize in data from patients. And they don't stop at simply classifying people. They are looking at their trajectories with the aim to have better clinical pathways for individuals and more personalized, really, diagnostic pathways and care pathways.
That is really interesting, how we can have AI to help all of this and help the NHS, right? Which seems like such a big jump, but it's not that big of a jump. Do you think this is the main reason why this research has gained so much interest in like the normal media outside of science circles and everything?
Yes, I would hope so. I really hope that we can make more advanced steps towards really translation into the clinic and translating really all the work we do in the lab, which is very exciting, into really social good and making a difference in the real world.
Definitely. Can this tool distinguish between different types of dementia?
Yeah, so this is where we are going. This is the next step. We started with looking at Alzheimer's disease because we started with training the model on data from Alzheimer's patients. We are now looking at many more cohorts, and with the initiative that we are working with the Turing and Alzheimer's Research UK, we will have patients that have many different disease subtypes. And now we can tailor the algorithms to identify actually which are the best tools and data we need for optimizing our predictions for different disease subtypes. We know already from preclinical studies, different dementia subtypes may relate more, for example, to gray matter or white matter loss in the brain, or many different other biomarkers. And that's where now our work is going in terms of optimizing the tools to be able to reduce the misdiagnosis, make it more precise on an individual level. And therefore then again, care pathway and treatment pathways can be more precise. And this can have also a huge impact on clinical trials. Because we see that drugs may not succeed, the clinical trials might not be successful, but that is potentially because we don't have good diagnostic tools. So the sample for the clinical trials is not well diagnosed. Therefore, you might not be seeing really a difference between your drug group and your placebo group, your control group, because they are totally heterogeneous rather than because the drug doesn't have an effect.
So better diagnosis is going to help the entire pipeline, from not just the diagnosis itself, but actually even the trials, even the drug discovery itself. I guess, are you also considering genetic markers in the patients? Because I guess that's how you get the truly personalized diagnosis.
Yes, yeah, absolutely. And this is really important also for disease subtypes. Getting genetic markers in dementia is actually quite hard. There is dementia that is very much kind of genetically defined, but we are making quite a lot of progress also in computational biology in terms of extracting polygenic risk scores that are very much linked to different disease subtypes, and this information will also be incorporated. We are hoping to be working on our current projects on looking, for example, in UK Biobank for healthy populations. And this is kind of the next generation of algorithms where we are looking at models that they are semi-supervised or unsupervised, and they'll allow us to work with data from populations that do not have a clinical diagnosis, but also by including genetic markers, we can make this diagnosis more precise. And again, look at these individual trajectories when people are very healthy, because that's what we are interested in. When people are in their 30s and 40s, we can actually identify their health trajectory, and then there is time for intervention. And we also believe that if our diagnostics are more precise, it will make a big difference in clinical trials, in terms also of drugs that have the potential to work much earlier at the stage of the disease. But currently, when people are recruited in clinical trials, they might be at later stages and the drug effects might be compromised because of the severity of the disease. Diagnostics is key, as you said, for the whole pipeline.
Thank you, Zoe. I was curious to know, just from what you said, are there ways that people can get involved or can participate? It's really amazing work what you're doing. I'm sure they'd be willing to volunteer in any way they can.
Yeah, no, it's really fantastic to see the interest from everybody. When the BBC picked up our work in the summer, it was really so wonderful, so encouraging. To see how many people wrote to say, can they volunteer? And yes, please. The Alzheimer's Research UK, the Alzheimer's Association, the Joint Dementia Program always advertise studies where people can participate. And it's really, we really need to work together to develop the data, to develop the algorithms, and it's really something that everybody can contribute immensely. And without without the patient data, really, no matter how many algorithms we built, we won't be able to translate this to the clinical practice.
Yeah, just get everyone to donate their brain scans. That would be nice. Out of, scientific curiosity, what's the most exciting result you've had so far with the algorithms that you've developed?
Yeah, so I think the most exciting result for me was when we could predict in individuals that very early in life had no symptoms, and we could predict whether they will remain stable and healthy or whether they are at risk for dementia. And it's really exciting, not because we're not interested in being able to diagnose patients better, but because this really has huge potential for the future. One could think that if we can build these tools and feed them with data that is not invasive, like, for example, digital data from, a Fitbit, it could really change the healthcare pathway. The same way that we have, a health check for cardiovascular disease, we could have a brain health check. And a lot of people then ask me, but what would I know in my 30s or 40s that I have dementia? This will increase, that I'm at risk of dementia. This will increase my anxiety tremendously. And I always say, see it the other way, which is actually you have the opportunity to change a lot in your lifestyle. And potentially these symptoms of dementia will never occur because, things sort of get delayed when lifestyle factors can really have an influence. And what we've seen from recent studies is actually that even predetermined factors, one could say, like, for example, polygenic risk scores, can express themselves differently by interaction with lifestyle factors. So really, for me, being able to diagnose or predict, actually, is not diagnosis, it's more prediction about health pathways, health trajectories very early on in healthy individuals opens up, I think, a very new kind of landscape, which is preventative medicine and really, health checks for everybody in this space, which I think could make a huge difference for so many people and families. So this has been really the most exciting. It was done so far in a limited kind of scale because we only had typically our research studies target patients. And so this was a study that targeted healthy individuals. But now, as I was saying, we do have UK Biobank and also with Alzheimer's Research UK, we are actually aiming to be able to develop these tools and then bring them into a general population and health checks. So very much before the disease appears in terms of symptoms.
So in a way, it's almost how DNA sequencing helped with preventing some types of cancer that were genetic. So you can do preventive and you can know about it so that you can do something about it before it's too late.
I really like that idea as well, what you're saying, because of course, our physical health is something that we pay a lot of attention to. And more recently, we've been looking more into mental health, but a brain health checkup is a fantastic idea.
Yeah, and it can have, I think, a lot of value in terms of, as you say, we get busy around our 30s and 40s, right? Running around and we ignore quite a lot of things that then will have an impact in later quality of life and well-being. Because, body and brain are really one thing. And sometimes, physical symptoms, we can get them more easily in terms of pain and you can see the difference. But brain, we tend to just stress and ignore, don't we?
Yes, if it doesn't stop us from working, then it's fine. Brain is fine. It will cope with it, future us will deal with all of this. And
Well, I think that's pretty much probably the end of the podcast. Thank you so much, Zoe.
I was just going to ask if you wanted to say anything else that we didn't ask before we say goodbye.
I think you asked everything, really. Yeah. So, to thank you for, having me here and really wonderful, to be able to talk about this. And I think anybody, the public and clinicians and machine learning experts, anybody can really help. It is very much a cross-disciplinary effort to really deliver anything we can that can resolve this, huge societal challenge. Thank you for inviting me.
Yeah, I think we're all looking forward to seeing the future of what this could bring and the future of what this research could and tool can develop into. I was just curious to know as well, in terms of people getting in touch with you, do you have, are you on social media? How can people kind of get in touch if they'd like to know more?
Yeah, well, I have to make a little confession. I'm not very good with social media because I can barely cope with my inbox and my email. So I hide a little bit, but very, very happy to take emails and very happy to kind of direct people if they want to know more or if they want to be involved in research studies or it's really very rewarding and very encouraging for all of the people involved in our teams because this is huge teamwork to see that this is of interest and it has an impact to everybody. So yeah, very happy to contact me. I have multiple email addresses, my Cambridge one, my Turing one, so I'm sure you can catch me anywhere. But I have to hide from Twitter to get some work done.
Okay, I was going to say I'll change the question, in fact, in that case. Could you tell us maybe some of the other organizations who are involved in this research project who perhaps people could get in touch with to know more about this kind of research?
Yeah, absolutely. So I hope the Turing will be one of the first. And I'm really grateful for all of the support that I've had from the Turing and really fantastic that we can really contribute to this effort. And then the University of Cambridge is the next kind of primary institute. Alzheimer's Research UK, we're working very closely with them as a charity, very much interested in this space. The EDON project, also the early detection of neurodegenerative disease project, which is spearheaded by Alzheimer's Research UK and supported also by the Gates Foundation. These are all places where people can find more information and also get in contact with various people working in the teams there.
Fantastic. Thank you so much again for coming to the Turing podcast.
Thank you for having me.
Thanks for listening to this week's episode. The show is hosted by me, Bea Costa-Gomez, Ed Calstri, Joe Dungate, Christina Last, and Anneca York. And the episodes are produced by Luca Lane. Music for this podcast is produced by Jam and Sun. You can listen and follow via the link in the description or by searching Jam and Sun on Instagram.